The universe is going to die. Not with fire, not with a bang, not with any kind of drama. It will die in silence. Over a period of time that your mind wasn't made to grasp, it will simply run out of things to do. The last star will go out. The last black hole will evaporate. And then absolute silence. Forever. For almost a century, that was the final answer. The end of everything. Then a physicist who won the Nobel Prize looked at this silence and said something strange. Wait, this isn't the end. This is mathematically identical to a new Big Bang. His name is Roger Penrose, and he believes that our universe is just a link in an infinite chain. That the radiation passing through your body right now, at this very moment, might be older than time itself. Not older than the Earth, not older than the sun, older than the beginning. I know how that sounds. Stay with me. The strangeness isn't in the conclusion. It's in the path leading up to it. And the path is made of physics that almost no one disagrees with. Imagine the last night the universe has to live. No stars, no planets, no light falling on anything, anywhere. Only cold distance and the long, patient nothingness that physics has been building. Since the very first fraction of a second after the Big Bang. To get there, the universe goes through eras. Today we live in the stelliferous era. Stars form, stars burn. But this era has an expiration date. Around 100 trillion years from now, at that point, the gas that gravity compresses to ignite new stars will run out. The last ones will be the red dwarfs, which live for trillions of years. But even they will burn out. Then comes the degenerate era. White dwarfs cooling down, neutron stars spinning slower and slower, black holes getting fatter with everything that comes close. And at some point, on timescales approaching 10 to the power of 36 years, even the protons inside ordinary matter may break apart. This process, proton decay, has never been observed. It's an open problem, and we'll come back to it. That leaves black holes, the last complex structures standing. But Stephen Hawking showed in 1974 that not even they are eternal. They leak particle by particle in what we now call Hawking radiation. A black hole with the mass of a star takes about 10 to the power of 67 years to evaporate. A supermassive one, like those at the center of galaxies, takes close to 10 to the power of 100 years. To give you an idea, compare that. The current age of the universe is about 13.8 billion years. That's roughly 10 to the power of 10. The time for the largest black hole to evaporate is 10 to the power of 100. It's not 10 times more. It's not a million times more. The exponent itself is 90 times bigger. The entire current age of the universe compared to that end is less than the first microsecond after the Big Bang. And when the last black hole finishes evaporating, absolutely nothing is left. A cold sea of photons and neutrinos spreading outward, forever through a structureless and futureless space. Physicists call this heat death. Entropy, the tendency of things to go from order to chaos, reaches its maximum, and nothing else can happen. The equations still hold, but there's nothing left to change. That was the end. Clean. Definitive. Until Penrose says, wait, heat death isn't the universe disappearing. It's the universe continuing forever in a state where absolutely nothing happens. The equations still hold, space keeps expanding, but nothing changes. No complexity forms, no event occurs, because every event needs a difference between hot and cold, between order and disorder. And heat death is exactly the state where all the difference has disappeared. So the universe doesn't end. It just remains for all physical purposes dead, while technically it continues. And forever here really means forever. Infinite nothingness. If you find that deeply unsatisfying, you're in good company. Because there's a question that this infinite nothingness cruelly highlights. Equations are great at telling you what comes after a state, but they have almost nothing to say about why the initial arrangement was what it was. Here's the game-changing point. The universe didn't start in just any state. It started in a state that, by any rigorous measure, was extraordinarily unlikely. Absurdly, almost impossibly ordered. The reason your coffee cools down and doesn't heat up by itself, the reason the past is different from the future, is that entropy increases. And it increases because the universe started with extremely low entropy. The past is ordered because we started from a point of extreme order. So if the universe ends in maximum entropy, and if maximum entropy is the most probable state of any system, why did it start in the opposite state? Standard cosmology doesn't have a clear answer. And the first clue as to where Penrose points is that maybe the question is circular. That the initial conditions of our universe weren't chosen from some external menu. They are the output of a previous cycle. Imagine you walk into a room and find a glass with ice on the table. But the ice isn't melting, it's forming. The liquid water turning into a cube by itself at room temperature. Nothing there violates any fundamental law at the microscopic level. It's just so unlikely that, in practice, it doesn't happen by chance. That room is the level of improbability with which our universe began, only bigger, by a margin that makes the glass of ice look like a guaranteed certainty. The Big Bang didn't start out messy. It started in a state of almost incomprehensible order. And that's counterintuitive. Thermodynamic disorder has nothing to do with how hot something is. It's about how many microscopic arrangements match what you observe externally. Despite its apparent ferocity, the primordial universe was in an arrangement that corresponded to a tiny number of possibilities. Penrose calculated this. To specify how fine-tuned the initial condition was, he estimated a probability of about 1 in 10 to the power of 10 to the power of 123. Read it again, because it's not 10 to the power of 123. It's 10 to the power of 10 to the power of 123. A number so large that if you wrote its digits at a rate of 1 per atom, the number itself would be much bigger than the observable universe. And the source of this improbability isn't what you would expect. It's not the primordial universe's smoothness, where background radiation's temperature is uniform in every direction to about 1 part in 100,000. The deeper source is gravity. For ordinary matter, the maximum entropy is the uniform distribution. The gas fills the box evenly. Gravity reverses that. Under gravity, uniform is not high entropy. The clustered state is. A universe in which all matter has collapsed into black holes has higher entropy than one with the same matter spread out smoothly. Gravity rewards clustering. In other words, the smooth primordial universe, which seems orderly on the outside, was actually in very low entropy, precisely because of gravity. It hadn't started to clump together yet. Penrose explains this using the well curvature, the part of the space-time geometry related to tidal forces. Black holes have extremely high well. The primordial universe had well close to zero. His well curvature hypothesis says that the initial singularity needs to have well equal to zero or very close to it. That's what defines the low entropy beginning on which the arrow of time depends. And what Penrose takes from this is straightforward. The initial conditions can't be arbitrary. Something selects them. And that thing, in his framework, is the geometry of the previous cycle. When someone proposes such a radical idea, the instinct is to ask if the person is outside the bounds of serious science. With Penrose, that instinct needs to be corrected immediately. In the 1960s, together with Stephen Hawking, he proved mathematically and rigorously that the formation of black holes is an inevitable consequence of general relativity. And once a massive enough object starts to collapse, there is no physical mechanism that prevents the formation of a singularity. It wasn't speculation, it was proof coming straight from Einstein's equations. Decades later, in 2020, Penrose won the Nobel Prize in Physics precisely for showing that black holes are a robust prediction of general relativity. He was 90 years old. The committee was not awarding speculative work, but rather something that shaped the foundations of theoretical physics for 60 years. Penrose called his framework Conformal Cyclic Cosmology, and he calls each cycle of the universe an aeon. The idea was fully presented in his 2010 book, Cycles of Time. The mainstream didn't accept it, but they also couldn't dismiss it outright because the mathematical core built upon things that were already well established. The geometry of light, the nature of scale, the behavior of space-time at its edges. And one of them is so simple and so strange that it's worth pausing on. It has to do with the fact that light, in a very precise sense, doesn't experience time. Special relativity says something that almost everyone vaguely knows, but has never really sat down to feel the weight of it. The photons. Light particles don't experience time. Not in a way that's different from ours, like a moving clock that runs slower. They don't experience time, period. A photon that travels at the speed of light experiences zero proper time passing between 2 points in its path. A photon emitted in the Big Bang 13.8 billion years ago that reaches your eye now. It experienced no duration between being born and arriving. From its point of view, it was emitted and detected at the same instant. The entire history of the universe takes up no duration at all from the perspective of someone traveling at the speed of light. This is not a metaphor. It comes straight from the mathematics of proper time. For objects with mass slower than light, proper time always accumulates. But at the exact speed of light, the term that measures this goes to zero. The photon doesn't age, doesn't tick, doesn't carry a clock. Why does this matter for a theory about the universe's end? Because of what the distant future is made of. After all the black holes have evaporated, after every massive particle has decayed or been absorbed, the universe is made almost entirely of radiation. Things that travel at the speed of light and, by definition, experience no time at all. The universe, in its final state, has lost all its clocks. Not in a metaphorical way. To measure time, you need a clock, and a clock needs an object with mass, something that accumulates its own proper time. A universe made only of radiation has no way to measure time, not because the clocks disappeared, but because the conditions that allow a clock to exist no longer apply. And here we get the first glimpse of the symmetry at the heart of the theory. The primordial universe, in that fraction of a second after the Big Bang, when the heat was so extreme that all particles were effectively massless, also had no effective clocks. Two universes without clocks. One at the start, another at the end. And if the physics at both extremes is structurally identical, maybe they're not as different as they seem. Do a thought experiment with me. Imagine two universes. In the first one, every distance, every wavelength has been multiplied by 1,000,000 compared to the second. Is there any measurement you can make inside either of them that tells you which one you're in? For a universe with massive objects, the answer is yes. A particle with mass has an associated wavelength, determined by its mass. And it doesn't increase just because the universe expanded. The electron has a fixed mass, so it has a fixed scale. Mass is what gives size its meaning. But in a universe without massive particles, only photons, there is no such reference. Every length scales together, and then the two universes, the large and the small, are physically identical in the sense that no experiment done inside them could distinguish one from the other. This is what physicists call conformal invariance. Physics doesn't change when you rescale all distances by the same factor. And Penrose's claim is that this is exactly the state that the distant future reaches, where the very idea of scale becomes meaningless because there's no mass to define it. The primordial universe was in a similar state for another reason. In the first fractions of a second, the heat was so extreme that the thermal energy overwhelmed the mass of any particle. The physics was approximately scale invariant. So the symmetry on which the theory stands is this. The distant future is scale invariant because the mass is gone. The beginning, because everything is too hot for mass to matter. Different mechanisms, but the same mathematical property. And for the theory to really work, for the map between the two to be exact, the distant future needs to have gotten rid of all the mass. That's where the most speculative piece of all comes in. Mass is not an intrinsic property of particles in the same way as charge or spin. And that's one of the deepest things the Higgs mechanism has told us. Before 2012, the idea that particles gain mass by interacting with a field that permeates all of space was theoretical. After 2012, when the Higgs boson was discovered at the Large Hadron Collider, with a mass of about 125 billion electron volts, it became established physics. The Higgs field is real, and the mass of fundamental particles comes from their interaction with this field. In a very early universe above a certain temperature, the Higgs field was in a symmetric state, and in that state, none of the particles that interact with it had mass. As the universe cooled and went through a transition, the field settled into its current configuration, the symmetry broke, and the particles gained mass. And now the piece that opens the door. The Higgs field is in an energy well, a minimum. But whether this is the lowest possible minimum, the true vacuum, or just a local minimum with a deeper vacuum somewhere else, is an open question. Running the standard model equations forward, the current consensus is that we live in a metastable vacuum, stable on cosmic timescales, but maybe not the deepest one of all. Penrose takes this a step further and makes it clear that this is speculation beyond established physics. He proposes that, in the extremely distant future, after all black holes have evaporated, the Higgs field may relax back to the symmetric state, not in a violent decay, but in a gentle and slow process that makes the mass of the particles disappear. Let me be honest with you, because honesty here is what separates this from pseudoscience. This is not confirmed physics. The standard model does not predict any mechanism by which the Higgs field relaxes on its own at cosmic scales. This is the weakest part of Penrose's framework, and he himself acknowledges it. But it's not an arbitrary invention either. It's connected to real and open questions about the stability of the Higgs vacuum. What matters for the central logic is this: if mass disappears in the distant future, then the final state of the universe is exactly scale invariant. And a conformal transformation can, in principle, map that final state to the beginning of a new universe. There's a hidden symmetry in plain sight, easy to miss because the two extremes seem opposite. In the beginning, the universe is hot, dense, and small. In the end, it's cold, empty, and practically infinite. But in the language of conformal geometry, which only pays attention to angles and the structure of light cones, and not to distances and durations, these two states have something in common. Both are dominated by radiation and are exactly or approximately scale invariant. In both, mass doesn't play an essential role, and absolute size has no physical basis. The beginning and the end of the universe are, in conformal terms, reflections of each other. The question is whether the mathematics of general relativity lets you make this identification cleanly, and the answer, surprisingly, is yes. The one who worked out the details was Paul Todd, a mathematician from Oxford, and his contribution is the technical heart of everything. The Big Bang's singularity in standard general relativity is a place where the curvature becomes infinite, where the equations break down. It's always been seen as a fundamental limit, but Todd pointed out something subtle. Not every singularity is equally pathological. Some are genuine physical breakdowns, others are just artifacts of the coordinate system, like the black hole horizon that looks like a singularity in certain coordinates and disappears when you change coordinates. Todd's insight was that the Big Bang singularity might be of this second type, that if you remove the scale information and look at the geometry of the Big Bang purely through the conformal structure, it might not actually be a real breakdown. It could be a smooth boundary, a surface that space-time can mathematically pass through. What he showed is that if the Big Bang really started with omega equal to 0, then the initial boundary of our universe is a smooth surface, not a singularity. And if the distant future of the previous aeon was in a scale-invariant radiation state, its future boundary is also smooth. And smooth surfaces can be identified with each other. The future boundary of the previous aeon becomes, through this identification, the Big Bang of the current aeon. I'll make the geometric argument more concrete because it sounds mystical until you see the mechanics. A conformal transformation is a change of scale that can vary from point to point, but it preserves the angles and with them, the causal structure of space-time. The light cones, the boundaries of what can influence what, remain intact, even when distances and times are rescaled. Now take the universe in the infinite future, full of radiation, expanding forever. Apply a conformal transformation that compresses this infinite future into a finite region. The endless expansion becomes a boundary, a surface you could draw at the edge of the diagram. Take the Big Bang. If its curvature is zero, it is also a finite boundary. Penrose's claim is that these two surfaces, the future boundary of the eon and the past boundary of the next one, can be stitched together. The infinite future of Universe 1 becomes the Big Bang of Universe 2, not through a dramatic physical process, but by recognizing that both are boundaries with smoothly compatible structures. And what crosses this seam? Only radiation. Only massless fields, photons, gravitons, maybe massless neutrinos. Massive matter, every atom, every star, every galaxy, doesn't survive. The black holes have already returned their energy as Hawking radiation before getting there. The information about the arrangement of matter is encoded in correlations in the radiation bath, present, but practically impossible to extract. The next eon then begins not as an explosion out of nothing, but as a continuation of geometry through a smooth boundary. A new universe that is born ordered, with entropy close to zero, because the smoothness of the seam forces this, and a new arrow of time begins to point forward. This structure is different from other cyclic cosmologies. Eon in Penrose's framework is not an oscillating universe. There is no big crunch followed by a bounce. Each eon expands from the beginning to heat death without ever contracting. The cycle doesn't happen at a turning point, but rather at the conformal boundaries. The chain extends infinitely backward and forward. There is no first aeon, there is no last. There has always been a universe before this one, and there will always be one after the next. Here the story leaves mathematics and enters something that can be tested. If there were events in the distant future of the previous aeon, and black hole mergers are among the most violent in any universe, these events leave marks on the boundary, and these marks cross the conformal seam into the radiation of the new universe. In 2010, Penrose, together with Varegozadian from the Yerevan Institute of Physics, published a paper claiming to have found evidence of this in the cosmic microwave background radiation. This radiation is the leftover heat from about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into atoms, and light could finally travel freely. It fills the entire sky with extraordinary uniformity, and its temperature variations have been mapped by the COBE, WMAP, and Planck satellites. The prediction is specific. If a merger of supermassive black holes happened in the previous eon, releasing a huge pulse of gravitational energy, that pulse spreads out in a circle. Compressed by the boundary between the eons, it should appear in the background radiation as a ring of abnormally low temperature variance. Not a hot or cold spot, but a region where the fluctuations are strangely subdued, compressed into a circular pattern. Penrose calls these rings Hawking points. Penrose and Gurzadian claimed to have detected these circles. Later work with collaborators like Daniel Wan and Christoph Meissner reported multiple Hawking points at levels between 3 and 5 sigma, which in physics are usually considered evidence or a discovery. If this is true, it is direct observational evidence of a previous universe, the most important cosmological discovery in history. But this is where it becomes controversial. Other groups have examined the same Planck data using different methods and concluded that the signals are consistent with standard inflationary cosmology, with no sign of cycles. The disagreement isn't about the circle's existence in the data. They do, and it's really about whether they're anomalous. It's a delicate statistical issue. When you look for many patterns in a huge sky, some will appear by chance, and calculating that probability is where reasonable physicists disagree. Groups like Moss, Scott, and Zeben argue that, taking into account this look elsewhere effect, the signals are not distinguishable from ordinary inflation. The data doesn't resolve the issue, but upcoming experiments might change that. The Lightbird, a Japanese satellite for measuring the polarization of the cosmic microwave background, and CMB-4, a ground-based project in the United States, will measure the sky with a precision that, in principle, allows for a much cleaner test. If the rings are there at the level that Penrose claims, these instruments should be able to see them. If they're absent, that greatly restricts the theory. For a moment, consider the space you occupy right now. Not in a philosophical sense. The literal volume of air around you, it's not empty. It's among the busiest places in the universe, in terms of the variety of radiation passing through it at the same time. Visible light, of course, but it's just a tiny slice of the spectrum. Radio waves are passing through your walls right now. Microwaves from your Wi-Fi. Infrared from every warm object near you, from your own body. The room isn't a quiet place, and you go through it without noticing because you only have an instrument for a narrow range built into your skull. But all of this is local and recent, generated by nearby sources in the last fraction of a second or in the last few years. What is in a completely different category is the cosmic background radiation. Here's a common misunderstanding to correct. It is not a distant wall of light at the edge of the universe. It is here, in this room, right now. Microwave photons from the cosmic background are passing through your body right now, at a rate of hundreds of millions per square centimeter per second. They don't come from one direction. They come from all directions at the same time, because they fill the entire universe uniformly. And these photons are old in a way that no other radiation you'll encounter in your life is. They've been traveling since 380,000 years after the Big Bang, when the universe was less than 0.03 of its current age. They are by far the oldest observable thing in our universe, and they're not in some remote place. They're here, passing through you. Now add Penrose's interpretation. If conformal cyclic cosmology is correct, the age we just gave to those photons isn't their full age. 380,000 years after the Big Bang is when they were last scattered. But the energy that produced them, the radiation field they're part of, didn't start with our Big Bang. It crossed the conformal boundary coming from the previous aeon. In Penrose's framework, it's radiation that predates our entire universe. The small temperature variations in that radiation, those ripples of 1 part in 100,000 that seeded all the large-scale structure we see, would contain, compressed within them, the residual glow of supermassive black holes merging in a cosmos that burned out and died before our beginning. The photons in your room would carry, if Penrose is right, postage stamps from a previous cosmos. The honest part, because it would be wrong to skip it, is that this is not confirmed. The Hawking points are disputed. There is a real possibility, maybe even likely given the weight of current opinion, that the fluctuations in your room are exactly what standard inflation predicts and nothing more, with nothing from before. But there is also the possibility that they are not. And that deserves attention, not because of Penrose's reputation, but because the theory makes a specific and quantitative prediction in a real data set that already exists. Let me finish at the very boundary itself, because that's where everything converges. Imagine that you could be present on the surface that represents the endpoint of the entire structure, where time, scale, and distance lose their physical meaning. You can't ask what it looks like, because seeing requires eyes, and eyes require brains, and brains require chemistry, and chemistry requires atoms that have already decayed. Nothing with mass survives up to this point. But you can ask what it is geometrically, and the answer is precise. It's a surface. Smooth, curved, conformally flat. On its side is the infinite future of a universe that has lasted for a duration too long to write down. All that history, every star that burned, Every civilization that rose and disappeared, encoded in the quantum state of that radiation field. Not erased, but in correlations so diluted that no one can read them. A complete and unreadable record. On the other side is the beginning of the next eon, a new space-time that inherits the conformal structure from the end of the previous one and uses it as its initial condition. A universe that begins with extremely low gravitational entropy, not because it was lucky, not because something from outside selected a special beginning, but because the geometry of the transition forced it. The boundary surface only allows one curvature. The apparent fine-tuning is not fine-tuning, it's a constraint. And here's what makes the idea beautiful. Regardless of whether it's right, the deepest problem in cosmology, why the universe began in an almost impossibly ordered state, is answered not by a selector, not by a multiverse, not by the anthropic principle. It is answered by geometry. The universe began in an ordered state because what it was born from was conformally flat at the boundary. And flat at the boundary means whale equals zero, which means low gravitational entropy, which means an arrow of time pointing forward, which means structure can form. Stars can burn, chemistry can happen. And here we are, having this conversation. I'll confess something to you, because it changed something in me when I understood it. I always treated the beginning as a wall, a point beyond which there are no questions, because there is no before. After I understood what Penrose is proposing, I stopped being able to see it that way. Not because he convinced me that he's right. He could very well be wrong about the details, but because he turned vague discomfort into a precise question. And precise questions, there's no way to get rid of them. Remember all that must go right for this to hold up. The proton needs to decay, and decades of searching haven't found that. The mass needs to go to zero, a process that the standard model doesn't predict. Dark energy needs to behave in a specific way. And recent data from the DES survey suggests that it might be changing. The prediction of Hawking points is disputed. None of this is resolved, and Penrose is clear about that in his own writing. And even so, the question doesn't go away. Inflation explains the smoothness of the background radiation, but it doesn't explain why the state before it already had the right properties. Conformal cyclic cosmology offers an answer. It may not be the right one, but it's a real answer, mathematically precise, physically grounded, and empirically testable. Even if Lightbird doesn't find any Hawking points, even if the proton never decays, the framework will have transformed philosophical discomfort into a geometric question that can be tested and, if wrong, discarded. That's no small thing. The universe may not end in silence. It may end in a transition, clean, geometric, and inevitable. The way a flame passes from one candle to another. Not the same flame, not a copy, a continuation, possible under the right conditions, without needing any mechanism other than the geometry of the passage itself. And somewhere in the impossible future of our universe, long after the last star has gone out and the last black hole has finished its slow evaporation, a conformal surface is forming. Silent, inevitable. The border between our story and the next. The end that serves as the beginning. The death that is, on the other side of geometry, birth. Penrose might be wrong about the details. He is almost certainly right about the question. And in physics, as in most things that matter, asking the right question with enough precision is already more than half the work. The rest is waiting for the data.